Probability trees, another fantastic resource by Maths for Everyone. So let's do this. Okay, I love probability trees because even though they're represented in a tree, we can represent them slightly different. Okay, so we're going to start with the basics. Now, a coin is biased. What does biased actually mean? Guys, so we're having a bit of a debate. First of all, no one knows what the word biased means, and that's okay. So, I don't know, did anyone ever want to be a magician when they grew up? Okay, because magicians, they use magic, right? However, I'm going to let you into some secrets. Their magic sometimes is trickery, okay? Because they, in fact, thank you, their magic is a bit trickery because sometimes it's like, you know, I don't want to reveal all the magician's secrets, but sometimes, I do know most of them, yes, but sometimes they use things to help you. So biased means, for example, you can get a coin and you flip it and you get heads or tails, right? Okay, and it will land on either heads or tails, or if you're really lucky, it will land on the third side, which everyone forgets about, which is that one there. Okay, I mean, who knows if that's really going to happen. So, in actual fact, okay, sometimes we have a biased coin because it's weighted. Have you ever heard of a weighted dice? It means no matter whatever you flick it, it will always go on heads. And it's because they put more weight on the side of the coin. So a biased coin means an unfair coin. The coin has been tampered with, so it's not balanced correctly. You can do that with dice as well. So whenever you roll the dice, it will be on a certain number. Okay, they're like dice. They're like magic. They call them magic dices. So you can say to your friends, right, okay, let's play a game. And you know that your dice will always roll on 6. So you say, right, okay, it's COVID, so everyone have your own dice. You have your dice. You know it's a magic dice. You play a board game, you always get a 6 because your dice is biased. It's not fair. Okay, so that's what biased means. Okay, so this is something we need to know. It's unfair. Okay, so when it's thrown, the probability that it shows heads is 2/3. So actually, it's got more chance of showing heads than it does tails. Okay. Now, for this purpose, we go with the assumption that a coin has 2 sides, and Dorcas throws the coin twice. Complete the probability tree. Okay, so probability is always out of 1. Okay, the way you have to see it, it's like it's out of 100%. Okay, it's always out of 1. So if we know this is 2/3 of heads, what do we have to add to get to 1? So it's tails. 1/3, exactly. So this becomes 1/3. Now, we throw the coin again. So for the second throw, we have these trees. These are called trees. I nearly put, oh my golly, what happened there? My spelling's got worse, I tell you. Okay, so these probability trees are laid out like this. Now I'm going to zoom right in so you can see how it should be laid out. So, here we go. So you throw a coin, you start here and you throw the coin. There's only 2 ways you can go. Please make sure you're watching the screen right now. You start here, you throw a coin, there's only 2 options. You either get heads or you get tails. Okay, Maz, flip it. We're going to say heads is the one with the cup of tea. I can't throw Maz, honestly, it'll be a disaster. Go on. Flip it. What did we get? Tails. Okay, guys, so guess what? We're going to go down the tails route. Everyone happy with this? Right, when I get to tails, I'm here again. Okay, so watch me zoom in here. I now flip the coin again. Have I changed the coin? No, it's the same coin. So my probability is still the same. Yes. So the probability of heads we know was 3 out of, oh, sorry, it was 2 out of 3. See, I'm just checking you guys are listening. And what was the probability of getting tails? 1/3. Perfect. Okay. However, I did not finish writing the whole thing. Okay, imagine I got heads in the first throw. So if I got heads, that means I'm here now, aren't I? And I throw it again. Okay, I throw it again. And is it still the same coin? So have the probabilities changed? No. Perfect. So this one was what? 2 out of 3, and this one is 1 out of 3. Okay, perfect. So this is how we fill in a probability tree. So there we go. We filled it in. Now, not every probability is going to be the same, every probability tree, because with this one, we use the same coin twice. What if on the next one we use a different coin? It might change here, okay? But does anyone notice anything about this probability tree and the branches and how we have written it? So we notice that each, like this part, adds to 1. This part adds to 1. This part adds to 1. So every time you draw a probability tree, you see this half a triangle, whatever it is. Well, it's a third of a triangle, 2/3 of a triangle. I don't know. What should we call this? Pardon? A branch. Okay, so each branch adds to 1. Is everyone happy with that? Perfect. Right then, so then the next part of the question says, find the probability that the coin shows heads both times. So let's think about it. We start here. Where did we go? What did we get? Heads. So we go up this way, don't we? What's our probability? So 2 over 3 and 2 over 3, because that's heads both times, isn't it? Whenever we say and in probability, it's a multiplication. So 2 over 3 and heads again, it's this branch. So 2 over 3. We multiply them together and we get 4 over 9. Right. The next one says, find the probability that the coin shows heads at least once. So heads has to be there at least once. Yeah? So is everyone happy? If you think about it, heads. Is that heads at least once? Yes, at least once. So do we have heads in there one time? Yeah, it can be more than one because it says at least once. Okay, how about heads, tails? Yeah, and tails, heads. Tails? No, okay, because I didn't even have heads in at all. Okay, so these are the 3 options. Heads, we already did here. It was green, wasn't it? Heads. We already know that's 4 over 9 because that's head and head. Yeah? So that's 2 over 3 times 2 over 3 equals 4 over 9. Done. Okay, the next one. Heads, tails. So if we start here, no, sorry, I want red. Heads, tails. If we start here, we go heads, which we know is 2 over 3. And then we get tails, don't we? So multiplied by, we go tails this way. What do we get? 1 over 3. So that's times 1 over 3. So that equals 2 over 9. Okay, and again, you can use a calculator, yeah? Last one is, we said tails then heads. So tails, we start here. We go down to tails. So tails, 1 over 3, multiplied, and then we got heads, didn't we? 2 over 3. So I love using colours for this. Okay, and this is 2 over 9. So now we have all of this. We have to think about, well, what does this mean? So we could have heads and heads, couldn't we? Or we could have heads and tails, couldn't we? Or we could have tails and heads, couldn't we? So we add them because in probability, or means add. So we're going to do 4 over 9 plus 2 over 9 plus 2 over 9, which equals 8 over 9. Now, what you notice is our probability should never exceed the value of 1. Ever. If it does, you know you've gone wrong. Okay? Because probabilities add to 1. Now, 8 over 9, what's left? What's left from 8 over 9? 1 over 9. So what is 1 over 9? The probability of getting tails, tails. And we could check that. What's 1 over 3 times 1 over 3? 1 over 9. So can you see that this adds to 1? And then when we multiply them all and add them all of that should then add to 1 as well. Okay? So what does this number 8 over 9 actually mean in terms of flipping the coin? Yeah, we're going to discuss this. This is what it means. It means if you flipped the coin twice, 9 times, theoretically, 8 of those 9 times, heads should appear at least once on each row. Okay? This question uses algebra. Okay, and that's fine because if we understood the first question, we should be able to apply that knowledge to this question. So give it a go quickly. Okay, so Jim has a biased coin. That means the coin is unfair, and that means the probability of heads and the probability of tails does not equal a half. Okay, that's what we definitely can say from that, can't we? From that fact. Then it says the probability that Jim will throw heads on any throw is P. Okay, so heads is P. And Jim throws the coin twice. So for every heads, it's the same coin. So these are all P as well. Okay, if you got to that stage, that is fantastic. Who did that? So what was the other fact I said? What do we know about probability? One branch adds to 1. Okay. So if you wanted to, you could write this. P plus something equals 1. What is that something? So P plus something equals 1. So what is that something? It's not going to be 1 over 3 because P plus 1 over 3 equals P plus 1 over 3. That doesn't equal 1, does it? Okay. Yes, we're going to need to minus P from both sides. And then we're left with something equals 1 minus P, aren't we? So tails is 1 minus P. Okay. Now, we could check that this is correct. P plus 1 minus P. Okay. Collect like terms. P plus P, blah, blah. P minus P is 0. And what are we left with? 1. This is true. So again, the coin is the same. We didn't change the coin. So all of these are 1 minus P. So we just literally, we know that this branch adds to 1. We just discussed that, didn't we? Yeah? How do we feel about this? Okay. Okay then. So let's actually now have a look at the rest of the question. It says, find an expression in terms of P for the probability that Jim will throw 2 heads. So, heads and heads means P times P. And what is P times P? Perfect. Okay. Then it says, given that P is 0.8. Okay, well, this makes it easier. They've told us P is 0.8. So everywhere there's a P, what am I going to write? 0.8. Okay, 0.8, 0.8. And what's 1 minus 0.8? 0.2, because 1 minus P is 1 minus 0.8. Does 0.8 and 0.2 add up to 1? Yes. So do you see how this works? We're just doing it in terms of algebra instead of numbers. So this is 0.2 and this is 0.2. Okay, perfect. So now we've written down all the probabilities again. It then says, work out the probability that Jim will throw exactly 1 head. Okay, let's think about this. How can we throw exactly 1 head? Only 2 options. We've got heads then and tails, or tails and heads. So, are we ready? Heads, if we start first and we do heads, we get 0.8 and then tails is 0.2. 0.8 times 0.2 is actually 0.16. Okay, again, you can use your calculator if you need to. Then, tails then heads. If we start at the beginning, tails is 0.2 times heads is 0.8, which is also 0.16. And then I can either do heads and tails or tails and heads. So what do I do with these two numbers? I add them together. Plus equals 0.32. So that's the probability of getting exactly one head. Because if I'm doing it once, I can either do heads and tails or tails and heads, right? Or. Okay, I love this type of question. It's just a free tree this time. It's got free. The branch has got free. Okay. But what I like about these questions is that we have colours. Okay. So I like to actually draw these. Oh, we have a red one, don't we? How many greens do we have? 1, 2, 3. Actually, it's going to wind me up that that's a different size. Red. 3 green and how many blue? Okay, perfect. So it says that a bag contains blah, blah, blah. Zanaf chooses a disc at random from the bag. She notes its colour and replaces it. Okay, it's really important. She has this mystery bag. She takes one out, she notes it down, and then she puts it back in the bag. So does the total amount ever change? No. That's something we need to know. Right, so red is 1 out of 6. Does everyone agree? I have 1 red out of a total of 6. Okay. So green, what is green? 3 out of 6. Now, some people might want to say it's a half. Leave it as 3 out of 6. It makes everyone's life easier if we leave them all over the same denominator. This is one time in maths that we do not simplify our fractions. All right? And then what was the last colour? Blue, and that's 2 over 6. Now, what do we notice about 1 over 6, 3 over 6, and 2 over 6? What do they add up to? 1. Okay, so then we have this branch, and we replaced it, didn't we? Okay. So that means we put it back into the bag. So do our probabilities stay the same for the next set of branches? Yeah? Perfect. So this essentially would be, again, 1 out of 6 is red. Green is still 3 out of 6. Blue is still 2 out of 6. And we're going to do the same for each branch, yeah? However, we're not going to do that question. I'm going to change it up a bit. Are we ready for this? Okay, so green, blue, red, green, blue, red, green, blue. Okay, imagine these are chocolates. These are Lindt chocolates now. You have the red flavour, which everyone likes. The green one, they've brought out a new flavour, it's mint. Okay, and then the blue one's got nuts in. Right, you've got a bag of chocolates. You've offered one to me. Okay, now, guys, we're going to start here. Now, follow what happens. If I start here, this is my bag of chocolate. I start here, right? And you've got a bag of chocolate. You give me, say, Miss, you're amazing. Would you like a chocolate? Take one. I put my hand in the bag. I take a red one. Where have I gone? Up this way, haven't I? Everyone happy? Right, so I've gone up here. Perfect. I've taken a red one out. And what do? I eat it. So guess what? This red is gone. Right. How many red do I now have in the bag? 0 out of? Pardon? How many are in the bag? Yeah, 5. Can you guys count to 5? Just taking the red Lindt chocolate and eating it. Out of 5. Okay. How many green are left in the bag? Out of 5. Okay, remember, I do not replace it because I ate it. Okay, and then how many blue are in the bag? Out of 5. Okay, brilliant. Done. Everyone happy? Right, now let's reverse. Okay, now we filled that in. Pretend we're still at the beginning of the... We're still at the beginning. Okay? Okay, imagine like it's the next day and for some reason you've got the same A lot of sweets. Okay? Or we're in a parallel universe and this is happening at the same time. However, in this parallel universe, you give me the bag of sweets, and the first one I take is green. I'll take a green sweet. So what am I going to do to my sweets over here? I'm going to take one away, aren't I? It's no longer free. I've just eaten one. You can't have it back to give to someone else. Okay, so tell me, what is left? How many red are left? Out of? Green. Blue? Okay. So you can see that from this, probability on my second branch is different, isn't it? If I do not replace, okay? Now, the last one. Right now, we're in another parallel universe, okay? And this time, what sweet do you think I took? I took a blue one, you know, went a bit wild, okay? So, got my blue one. If I took a blue one, what does that happen to this pile of sweets over here? I'm going to take away this blue one, aren't I? And can you see how easy this is? That even though we're doing this mathematics, okay, it's actually, I've just drawn some colourful dots. And all I'm doing is taking away and counting to 5. So, how many red do I have? Out of? How many green do I have? Out of? How many blue do I have? Out of? So can you see how when we do not replace it, the second tree, this is why we have to read the question really carefully. Okay? So when it says it does not replace, our second branch is going to be different. We've just shown that it's different using sweets. Another thing you should check is that so this is one branch here, isn't it? This is one branch. Okay? Does that add up to a whole one? Yeah, 0 over 5 plus 3 over 5 plus 2 over 5 is 5 over 5, which is 1. Okay, this branch is my middle branch. Does this one add up to a whole one? Yes. Okay, and this branch, my third branch, does this add up to a whole one? Yes. Remember, each branch needs to add up to a whole one. It's really important. Okay, now I have no idea what the second part of the question is because we hijacked this question, didn't we? And we turned it into something different. Okay, question 4. Oh, it's okay. It's a completely different question. That's fine. Right, go on, give this a go. Okay, question 4. Linford and Alan race against each other in a competition. If one of them wins the race, he wins the competition. If the race is a draw, they run another race. They run a maximum of 3 races. Each time they race, the probability that Linford wins is 0.35. Each time they race, the probability it's a draw is 0.05. So each time they race, the probabilities are all the same. What does a branch add up to? 1. So what's this probability? Absolutely. Okay, so 0.35, 0.05, 0.6, 0.35, 0.05, 0.6. Everyone happy? Perfect. It says calculate the probability that he wins the competition. Now remember, there's a few different ways to win. First of all, it says if one of them wins the race, he wins the competition. Okay, and we're talking about Linford. So there's only a few possibilities this could happen. Right. He could either, on race 1, Linford could win. And then the competition's over. He won, right? So we know that's 0.35. Or they could draw on the first race, and then Linford could win on the second race, couldn't he? So draw and win. Then for the last one, the other possibility, he could draw on the first race, draw on the second race, and win on the last race. These are the only 3 possible options for Linford to win the competition. So draw and win. Okay? Anyone know what 0.05 times 0.35 is? 70, 40, 175. Is it 0.175? Is that right? No, 0.0175, isn't it? Oh, I'm so confused. What is it? What's 0.05 times 0.35, please? 0.0175. I knew I was close. I forgot the zero. And then multiply that by 0.05 again, please. Okay, and this one comes in standard form. So just a quick recap of standard form on your calculator. To the power of -4, so we know it's a decimal, because it must be 0.0. We move the decimal point 4 places. 1, 2, 3, 4. The decimal point is now here. We fill in the zeros. The 0.000875. Okay? Now, he could either win in the first race, or win on the second race, or win on the third race. So I need to add these three values together to find the total probability that Linford wins. So this plus 0.0175 plus 0.35 equals 0.368375. And if we did to 2 decimal places, 0.37 to 2 decimal places. However, it will tell you what to round to. Okay? Okay, question number 5. Now, I'm really excited because you're going to do this all on your own. I'm not going to explain it. I'm just going to give the answer. However, just a heads up, guess what? He does not replace it. We've already done a similar one like this. You've got this, everyone. Okay, then. So so you should have done the question. So let's do this. 4 out of 9, then 3 out of 9, 2 out of 9. Okay, he does not replace it. So I know now if he takes one and doesn't replace it, these are all out of 8. Everyone should be happy already writing out of 8. And then he takes a red. So that means it's my red that changes here. This becomes 3 and everything else stays the same. Then on the second one, it's the white that changes. So my red stays the same as the first one, and my white now becomes 2. And then for this one, everything stays the same as the first branch, apart from my blue, because that's one I took, which becomes 1. Okay, so everyone should be happy doing this. It says calculate the probability that one of Sanjay's beads is red and the other is blue. Okay, so where is red and blue? Red, blue, or blue, red. Yeah? So we have red, blue, or blue and red. So red, blue is 4 over 9 times 2 out of 8, which is 8 out of 72. And then blue and red is 2 over 9 times 4 out of 8, which is 8 over 72. I then need to add these together because it's red, blue, or blue, red, right? These are the only options to get red and blue. And I get 16 out of 72. So, question 6. Peter wants to pass his driving test. The probability that he passes at his first time is 0.7. When Peter passes his driving test, he does not take it again. So if he passes, we won't need to draw another tree here because there will be no need to do a pass or fail. And think about the context of the question. If you passed your driving test again, would we actually do it again? No. So there would be no tree there. Okay? If he fails, the probability that he passes on his second attempt is 0.8. So we know this is 0.8. Now we have all the information and common sense, okay? Because it is common sense, isn't it? If you pass your driving test, would you take it again? Of course not. That's not how the world works, okay? And you have to remember, when we're doing mathematics, we have to bring the context into it. And when we start looking at A-level mathematics, it is all about context, okay? We need to actually think. We're not just doing a process. We need to think about what's happening. So, what do we also know? That this probability, if your pass is 0.7, what should this be? 0.3, because probabilities add up to 1. And then the same for this branch, 0.8 and 0.2. Perfect. So step 1,
fill in the branch. Perfect. Done. Then it says, calculate the probability that Peter needs exactly 2 attempts to pass his driving test. If he needs exactly 2 attempts, okay, what does that actually mean? He has to fail and then pass. Absolutely. So fail and pass. That means I do fail 0.3 and pass 0.8. So 0.3 multiplied by 0.8 is 0.24. Okay. Then, calculate the probability that Peter passes his driving test at his 3rd or 4th attempt. Now, so we technically, our tree would technically keep going, but only on the fail. We have pass, fail, wouldn't we? And we know it said 0.8, 0.2 was what it was after that, okay? So, for 3rd attempt, what do we have? 3rd attempt would be fail, fail, pass, which is 0.3 times 0.2 times 0.8, which is 0.048. Yeah? And then we could do for the 4th, fail, 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 pass, which is 0.3 times 0.2 times 0.2 times 0.8. Remember, because I'm going down here, look. 3, 2, 2, 8. So when I multiply all that, is someone checking my multiplication? Because I'm just doing this in my head. 0.0096, is that right? Yeah, perfect. Now, it's either fail, fail, pass, or, which is code word for plus, fail, 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 pass. So I need to add these together. 0.048 plus 0.0096. What is that probability, please?
0.0576.
Perfect. So the answer is 0.0576 when I add them. And there we go. We have now done question 6. That's a 7-mark question. This question, getting this question right, it can actually be the difference between a grade. Okay, question 7. Now, these are my favourite type of questions because, again, context. Context. Okay, here we go. There are 6 milk chocolate and 4 plain chocolates in a box. So, first of all, milk chocolate, 6 out of 10. Plain chocolate, 4 out of 10. And do you remember I said in probability it's best not to simplify the fractions or change them to decimals or anything like that? We can, but it's better not to. And you'll see why. Right, so I'm going to call milk chocolate blue. Plain chocolate red. Everyone happy with that? So, 6 milk chocolate. 1, 2, 3, 4, 5, 6. How many plain chocolate? 1, 2, 3, 4. Everyone happy? I've drawn a diagram. Now, the thing that I love about mathematics is I love drawing. I'm not very good at it yet. However, I love it. So I do like to draw. It says, Rob takes a random chocolate from the box and he eats it. He's put it in his mouth, it's gone. Right? So here we are. Let's pretend to be Rob. Here I am, I'm Rob. I've got 2 choices. What does Rob choose first?
Milk.
He chooses milk. Okay. I eat a milk chocolate. Guess what, guys? I'm going to get rid of one of these. If I eat a milk chocolate, how many milk chocolate are now left?
5 out of 9.
5 out of 9. How many plain chocolate are now left? 4 out of 9. Okay then, so do you know what, guys? I'm going to pretend I'm back here. Like there's nothing happened. We're going back to the start. Rewind. I've got a time machine. I've gone back. Okay. So, right. This time, Rob didn't go for a milk chocolate. What did he have? He had a plain chocolate. Right. So now I've taken a plain chocolate. What is the milk chocolate? 6/9, of course. And the plain chocolate? 3/9. Wow. This is how we fill in the tree diagram. Does it make more sense when we draw the picture and we think about the context in a real life fashion? Right then, so work out the probability that there are now exactly 3 plain chocolates. Where are the 3 plain chocolates? So it means what's had to happen, that Rob's had to have plain, okay? Oh, and then you're saying that now, this is really naughty, guys, you're getting it wrong. Are you now saying that Alison took a plain? Because if she took a plain, how many plain chocolates are left? 2. If there were 4 to begin with, if Rob eats 1, how many are left? 3. If Alison eats 1, how many are left? 2. This isn't what we want. Guys, think about this. They're trying to trick you. Right, that's wrong.
No, Mrs. MP.
So, there are 3 plain chocolates left if we get to this stage.
What did I say?
Okay? Or we get to this stage. Think about it. Think about it. Yeah. There's only 3 plain chocolates left if we do this one and this one, or this one and this one. Okay? Think about it for a second. Right, the only way to do this, if you still don't understand how there's 3 and 3, draw a picture and start here. Rob takes 1, and then Alison takes this one. How many plain you got left, okay? However, we've just had a discussion as a class. As we know, maths is better spoke about. So this is what we're doing. So we're going to do. So this is 6/10 and 4/9, which is 24/90. Plus, because it's or, we could have done 4/10 times 6/9, which is also 24/90. So I get 48/90 is the probability of that. Just over half. Okay? Well done. Now you have the basics. You will be able to finish off all of these questions, and you can use Maths for Everyone to look at the worked solutions, which is fantastic.